Have you ever wondered how your computer actually sees the world? I mean, it's not in pictures or words, it's in a kind of secret code. Well, today, we're going to crack that code. We're talking about hexadecimal. It's the language that connects our human brains to the raw, binary heart of a computer, and we're going to demystify it once and for all.
So, let's start with a pretty basic problem. Computers and humans are, well, terrible at talking to each other. We operate on completely different wavelengths. And anytime we want to peek under the hood, look at a specific memory address or a raw piece of data, we just hit this massive language barrier.
I bet you've seen something that looks just like this. If you've ever done any web design, or messed around with graphics, or looked at a CSS file, you've run into these color codes. It starts with a hashtag and then has 6 characters. That, right there, is pure hexadecimal.
But have you ever stopped to think about what that jumble of letters and numbers really means? I mean, it looks kind of random, right? But it's actually a very specific, superstructured piece of information. And together, we are about to decode it.
Okay, so here's the real issue. Computers think in just one way, ones and zeros. That's it. That's binary, their native language. But for us, trying to read or write these long strings of binary is an absolute nightmare. That one little color code would be this endless, mind-numbing sequence of ones and zeros. You'd make a mistake so easily. Clearly, we needed a better way.
And that better way, you guessed it, is hexadecimal. It's this beautiful, elegant solution that became the standard across the entire industry. And for a very good reason. It's a perfect fit for the way computers are built.
So what is it exactly? Well, hexadecimal, or just hex for short, is a base 16 number system. Now, we're all used to base 10, with our 10 digits from 0 to 9. Hex just kicks that up a notch and uses 16 unique symbols. And its entire purpose in life is to be a clean, compact shorthand for all those messy ones and zeros.
So you might be asking, how in the world do you get 16 symbols when we only have 10 digits? It's actually a pretty clever trick. After we run out of numbers at 9, we just borrow the first 6 letters of the alphabet. So the number 10 becomes A, 11 becomes B, and you just keep going all the way up to 15, which is F. Simple as that.
And this right here, this is the superpower of hexadecimal. This is why it's so important. A byte, which is that fundamental unit of computer data, right? It's made of 8 bits. And because hex is base 16, it has this magical property. Exactly 2 hex digits can represent 1 full byte. It's a perfect one-to-one mapping. No messy leftovers, no weird conversions, just clean, simple, and perfect.
And this chart really shows you why hex is king compared to other systems, like octal. See, octal is base 8. So it tries to group binary into packets of 3, but when you divide an 8-bit byte by 3, you get this messy remainder. It doesn't fit. Hex, on the other hand, divides that same 8-bit byte into 2 clean, perfect 4-bit packets. That perfect division is everything.
All right, so the theory is great. We know why hex is the standard. Now, let's get our hands dirty and actually learn how to translate between the computer's binary language and this awesome hex system.
The whole conversion process is really just a simple 3-step dance. First, we chunk the binary into small groups. Second, we translate each of those chunks. And third, we combine them all to get our final hex number. Let's walk through it. Okay, let's take this pretty intimidating-looking binary string as our test subject. Right now, it just looks like a total mess of ones and zeros. But trust me, by the end of this, it's going to make perfect sense.
Step 1, we chunk it. And here's the key. You have to start from the right and group the binary into packets of 4. And these little 4-bit packets have a pretty great name. They're called nibbles. So we take our long string and just break it down into these 5 neat little nibbles.
Now for step 2, the translation. We're going to use a really simple trick for this called the 8-4-2-1 rule. See, each of the 4 spots in our nibble has a value. The first one's worth 8, the second is 4, then 2, then 1. All you do is add up the values where you see a 1. So for that second nibble, 1, 1, 1, 0, we add 8 plus 4 plus 2. That gives us 14. And if you remember our chart, 14 in hex is the letter E. We just do that for every single nibble.
And finally, step 3, combine. We just line up our new symbols in the exact same order. And there it is. That crazy long binary string becomes the much shorter, much easier to read hex number, 9ECA1. See, we cracked the code. Okay, so converting is one thing,
But how do computers actually work with these numbers? To really get it, we need to look at a basic operation, subtraction in binary. Now, most of it is super easy, but there's this one tricky part called borrowing. If we can master that, we'll get a way deeper look into how computers actually think.
Look at these rules. The first three are exactly what you'd think, right? 0 minus 0 is 0, 1 minus 0 is 1, no problem. But that last one, 0 minus 1, that's the troublemaker. To solve it, we have to do something you probably remember from grade school. We have to borrow from the column over to the left.
But what happens if you need to borrow from a 1 that's way over on the other side of a bunch of zeros? This is where a fantastic shortcut called the borrow ripple comes in. It's just a simple pattern. First, that 1 you're borrowing from turns into a 0. Next, all the middle zeros you had to jump over, they all flip to 1s. And last, the 0 you were stuck on becomes 10, which, remember, is the number 2 in binary.
So when we use that shortcut, our tricky problem of 1000 minus 1 suddenly becomes easy. The final result is 1001, which is just 7 in decimal. We skipped all that confusing borrowing stuff just by applying one simple, elegant pattern.
Okay, let's bring this all together. By getting a handle on how to translate between human-friendly hex and machine-native binary, and by understanding how computers do basic things like subtraction, you've basically just gained a new kind of digital literacy.
From now on, you can look at a memory dump, or a network packet, or even just a simple color code on a website, and you can understand the real binary information it represents. You're not just looking at random characters anymore. You're actually reading the true language of the machine.
And that's what's so cool about this. This isn't just some abstract mental exercise. It's the key to understanding the fundamental building blocks of, well, all digital technology. So the real question I want to leave you with is, now that you can read the code, what are you going to build with it? Thanks for watching.